Again, second day of the definite integral. We're studying area between a curve and the x-axis, right? And these are funny shapes, like in geometry you had rectangles and triangles and all that stuff, right? But now we're doing curves where we don't have a defined shape. But sometimes it happens so that we get a problem where we can use geometry, but you have to recognize, boo. Better recognize, boo. That shape right there can also be written as an equation like this. Do you remember what shape that is?
Circle. Oval.
It's a circle.
Circle.
Yeah, so we have a circle. The radius is
What? 5.
5, square root of 25. The center is 0, 0. Okay, so really what we're looking at with this problem is a quarter circle of radius 5.
Wait, why doesn't it go complete circle?
Because this is from 0 to 5. Right? So you do not know how to calculate this algebraically. Frankly, we never get to that. But you do know it geometrically. So how would I calculate this value geometrically? Yeah, 1/4 pi times 5 squared, right?
45 pi over 4. Indeed.
And you have your answer.
Do we ever have this kind of look like?
I would leave it alone.
Where's the 1/4 pi?
This is circle area. Area of this quarter circle is 1/4 of pi r squared. So 1/4 of pi times the radius squared.
We can't do that algebraically because we can't do the antiderivative of that? No?
Correct.
You can't just make it.
There are, so this is a chain rule, right? You've got a function inside and then the 1/2 power. You don't have the tools to solve that antiderivative, to calculate it. Right, so that was from the homework. Nobody asked about it, but it usually comes up. So let's see. Do you want to see another sine cosine one, or are there any of them that you want to see an integral of? So you could do.
Will you ever have?
Do you want to see? I mean, we're looking at. You could do linear, quadratics. We could do sine, cosine. We could do e. Do you want to see any of those functions as an integral algebraically?
Would you ever have to do like cubed function?
Cubic?
Yeah, cubic.
Yeah, let's do cubic. The answer is yes. Just something like this, right? Now, we cannot tackle that geometrically because it's a curve that's not consistent. Circles are curves that are consistent, so we can do those geometrically. Right? Okay. What do we got here? Antiderivative?
3x or x.
Over 3. Oh.
Right? Add 1, divide by it.
We need to make a complex system.
Don't forget, Damon, to evaluate.
I always forget to evaluate.
Do you have to find the integer every time? Like every single?
If this is the, if you're doing that, yeah.
So even if you're graphing for doing it that way?
It's very rare once we get rolling here that you'll do it graphically, to be honest. Yeah.
I do not.
It's just, what's the derivative of this? 4x cubed over 4, right? And it gets you back here. We're just working.
Because then you just cross that word forward.
Here you cannot, but up there you go. Yeah. Okay, now evaluate. So you get 2 to the 4th over 4 minus 0 to the 4th over 4.
4 minus 0.
2, 4, yeah, 4.
Those ones would be a box or a circle.
That's neither.
Well,
A circle.
Vertical.
Squircle.
Oh, square circle.
Okay.
Okay.
Any others you want to see? Can you think of a function that you?
Will we have to do it where there's 2 loops inside? Like we've done it with the sine ones where they're the same, so they just cancel out, but will they ever not cancel out?
What?
So, we've done it with the sine equation where it loops from negative to positive. Will there ever be a time where those won't cancel out?
I don't know what you're asking. I'm sorry.
So you know,
I know sine, it goes sine, cosine. Oh,
when it goes like this
Oh.
and how there's under the x-axis?
so you're thinking,
Yeah.
What happens?
and you're asking if there will be a time where that doesn't cancel out?
If they don't cancel each other out, because if the subset's given where it covers both loops.
Right. So this would be say 0 to 2 pi. That would be 0, the area. Okay. So yeah, I could ask you what is the area from 0 to pi. Give you an answer.
But if there's an even amount of transitions, will it always be
Right.
0?
Yeah.
Even if it's another equation of the sign.
As long as there's an equal amount of area top and bottom. Yeah. You want to do a sine?
Yes, please. I'd rather know how to do it than come across it and avoid it.
This is very straightforward. Jason.
Here, you can finish that.
Okay. Antiderivative of sine? What? And then evaluate. Cosine at pi?
Yeah.
That's sine at pi is 0.
Oh, one. Feels like it's like a stop.
Cosine at 0.
1. No, yeah.
Yeah.
Why?
Here it is, hesitant.
So it is
Don't do that, Mr. Arthur.
So it is zero.
Wait, isn't it a
So it
negative
would be
1
zero.
though? At pi?
Cosine at pi is -1.
Yeah.
So that should be positive. So it should be 2. Yeah.
Wait, what?
Cosine at pi is -1.
Oh, okay.
So the negative of -1. Yeah, I don't know why that slipped past me.
Because
Oh, I didn't write any of
Okay.
it down. I said
yes, David, yes.
Let's look at an absolute value.
Okay.
Hold on, 3 seconds.
1
Wait.
2.
How'd you get to 4 on that one?
here.
I'm still stuck.
Where are you stuck?
I don't. I
Do,
don't know.
do you understand the antiderivative?
Yeah. I just don't know how to
Then you
get.
plug in the.
I'm stuck on
Oh,
that
that's a
one.
0 and that's a 0.
Can you understand plug 2 in,
Yeah.
and plug 0. This is just arithmetic. 2 to the 4th is 16. Divided by 4 is 4. 4 minus 0.
Oh. I was just doing too much.
No, you have to use the function.
I ignored the explanation.
Yesterday,
We learned.
we did this problem. Fontaine, are you alright? I'm so bored. It's on Classroom if you want to start the assignment. We did that problem yesterday, right? We got 2.5 as the area. Okay.
Wow, you remember well.
Do you want to put that on the test so I can remember well?
It only works if you can remember.
You know, Hunter, I actually can. Don't fight.
What's the difference?
Well, now it's not
That's only gonna be the top.
vector thingy.
That's gonna create a V. It should, right?
It should.
It's gonna create a cusp.
No, it's not a cusp.
No.
Not a cusp, because it does come with.
It's a corner.
Oh.
So it's still, the positives do not change. So this is all positive, correct?
Yeah,
Okay, so we were going to go from here to here. And that's not going to change. Because it's all positive. But what happens when we get in the negatives? With absolute value, what does it do to negative?
Goes positive.
It makes it positive. So this is going to come up here now. So everything is now positive.
Ah,
Right.
we're watching a fireworks.
So instead of the negative part, it just flips it over the axis.
so then would it be 5? The area would be 5?
There's not 5.
No.
Because they're not the same.
Oh.
Okay. So that's what absolute value does. It flips it over the top. Okay. This area is 3 times 3, 9, 4.5. Plus 2 times 2 is 4 divided by 2 is 2. So we get 6.5 in this case.
Wait, what's
This area.
So it's 1/2 times.
3 times 3. There's what geometrically what an absolute value will do for you. Makes everything so positive and lovey and touchy-feely. Okay, algebraically, how do we work on this one?
With the absolute value.
We have to split it up where there were positive and negatives. Okay, so 0 to 3 is where this was normal, right? So that just gives us 3 minus x. Okay. So that's normal. But then this part that was negative,
3 plus
3 to 5, right? 3 to 5.
absolute value.
Negate the function. 'Cause this function will give us a negative area, right? What happens if you multiply it by a negative? It gives you a positive, right? So in effect, we're doing a negative times a negative here.
But the other function will be.
This?
Yeah.
No, this is positive
Why?
because it's positive. It's above the x-axis.
What's the other one?
The other one is not over here. So see how I removed the absolute value bars?
Correct.
So when I do that, it becomes this function. And I have to negate it to make it positive. Okay. So that's how you deal with absolute value. Multiply by a negative. That's it. Wherever this is supposed to be negative, that's what you do. And then algebraically, you can go figure that out again. Okay. So what's the antiderivative of this?
3x minus x squared over 2.
Plus, or do you want me to just make it a minus?
Yeah.
Doesn't matter.
It makes would it be easier?
Negative 3x minus x squared over 2, 3 to 5. So absolute values give you a little bit more work to do, right? But not that big a deal. So 3 times 3 minus 3 squared over 2. If you don't want to put 0 evaluations in there that are 0, don't worry about it. I put it here just to show you. Okay. So normally I wouldn't write this here. And that's got to be in big parentheses because that negative has to travel. But if you do all that work, you're going to get 6.5. Okay.
Does an absolute value, like sign, transfer over into the antiderivative?
No, you have to rewrite the problem without the
that.
absolute value in it.
Okay.
That's what I'm trying to get you to see.
Okay.
So rewrite the problem without absolute value in it, then do that. There's no way to calculate antiderivative of absolute value of x. Okay. That's how we deal with absolute value. Same with thing we do with limits. Questions? A little bit more practice tonight is all.
Is this gonna be a long thing? We don't have one sheet of paper, right?
No,
We're one sheet of paper covering?
probably. No guarantees, but
Probably not.
How did you write?
No. Fine.
Yeah, so you're
I'm gonna
okay. So it's
try.
only 5 problems from 5-2, and then 6 spiraling problems. Shouldn't be a big deal. And you have 20 minutes, so hopefully you can finish most of this now. Please ask any questions you might have.
I need a lot of questions.
You guys are